the SKA era. We are starting at 5 minutes past 14:30, so we shift our clocks by 5 minutes. Floor is yours. Thank you.
Thanks a lot. So let me start by thanking all the organizers for this opportunity to speak. So this will be, I will be talking about an era, and also the following two talks will be on similar lines, I guess, about an era which is slightly different from what you heard so far. So there is one part in structure formation where we study a lot about the CMB, which has given us a lot of information. The other part is from the relatively low redshift universe that comes from the galaxy surveys. And there is this gray area, which is kind of still relatively like less probed by observations at least. And this is something which we would like to know observationally what is going on to complete this picture, starting from CMB to how the galaxies formed and how they evolved, and then how the universe accelerated to the present epoch. And this is also very interesting for us because within this unknown gray box, there would be a time when the first galaxies or the first stars, first luminous sources in the universe would have formed. We again still don't know what kind of redshifts are we talking about or what exact redshifts are we talking about, but probably it will happen somewhere between 15, 20, 30, depending on who you talk to, and this is something we would like to understand. And as we will discuss, at present observations are slowly giving us a glimpse as to what might have happened in this era, and things are already quite interesting. I mean, it is already telling us that there are various things which we don't understand. Now, to probe this era, there are kind of two broad ways of probing it. One is through the galaxies, and these are, by the way, simulations. The left one is a standard n-body simulation, which shows how the structures form. So starting at the early redshift where things were homogeneous, I mean, gravitational instability will form the cosmic web, and then there will be very high density regions where eventually the galaxies will form. The right-hand side shows the movie of the neutral hydrogen from a model, let's say, and it shows how the neutral hydrogen gets ionized as these galaxies give away ionizing radiation. And as we will see, these black regions are the ones where ionized so-called bubbles form. They roughly trace the regions where eventually galaxies would form. So you can probe this high redshift universe either by looking at the signatures of these galaxies, maybe try to detect them directly, or try to go into the intergalactic medium and detect signatures from this intergalactic medium, in particular through the neutral hydrogen. And because this neutral hydrogen, their kind of structure, the distribution traces the underlying galaxy distribution, we hope to learn about how these first galaxies would have formed by studying neutral hydrogen. Now, this epoch, which is known as the epoch of reionization, it carries immense importance, and my previous slide would have given you the idea. What I'm going to tell you now is that we can study the formation of the first galaxies through these kind of observations and modeling. Properties of these early galaxies, what kind of feedback processes may have played, how did the universe get chemically enriched, and so on. But it can be interesting for cosmology as well. You probably will have information about the halo mass function at these early redshifts. Maybe these ionized bubbles know about the properties of the cosmic web into which they are expanding. And in particular, often things which are interesting to others that these models may help in either detecting or maybe putting limits on non-standard extension to our concordance model. These era are now being probed by a variety of observations, and this is just a kind of representative list. One is trying to probe it through quasar absorption spectra at high redshift, through high redshift galaxies, through CMB anisotropies, and we have also started kind of understanding it through the 21 centimeter signal, and we hope to, this is probably the future of the field. Now, if you think about the physics which go into trying to understand these first galaxies and the epoch of reionization, there are various ingredients. And again, I will give you a broad overview of the kind of ingredients that are needed to kind of model and understand these era. Of course, we are talking about the galaxy formation, and galaxies would form in dark matter halos. So that is usually the starting point. And within these dark matter halos, we know that the gas or the baryons will basically be attracted by the potential of these huge halos. And eventually, there will be a lot of interactions between the gas. They will cool, they will fragment, maybe feedback effects. We will have galaxy and star formation within these halos. They will produce stars. We will have the stellar spectra. Maybe we will try to calculate the ionizing photons, which will eventually affect the intergalactic medium. And if we understand this part, the hope is that we will be able to predict the properties of the first galaxies, let us say the galaxy luminosity function. And then with the kind of observations I will talk about, one will probably be able to kind of nail down this part about how these galaxies form. But there is another part of the story where after these galaxies form, these ionizing photons which the stars would have formed, they will probably now have to escape from the galaxy. And we don't know whether they escaped, how did they escape, what are the conditions which help them escape, and so on. And once they escape, how do the ionization fronts propagate through the intergalactic medium? That's a very difficult problem to solve, and that's to do with the radiative transfer. And after you have modeled all these things, you will calculate various observables to match your model with different observations. You will do statistics and so on. So this is roughly the ingredients which go into understanding these first galaxies and reionization. That is not to say that we model everything in full detail when we try to understand the observations. We try to make approximations and simplifications in various stages depending on what kind of questions you are trying to answer. But roughly, this is the physics which one is trying to at least understand. And broadly speaking, this whole kind of flow chart can again be divided into 3 blocks. The dark matter halos are something which people working on cosmology and structure formation do all the time, either through n-body simulations or analytical methods, so on. And then there is this part which has to do with what is happening inside the halos, what is happening to the gas inside these halos. So let's say galaxy formation, interstellar medium, how they talk to each other. And the final thing is how these galaxies are affecting the intergalactic medium, the surrounding gas. It could be hydrogen, it could be other things. Although I showed these 3 blocks and made these arrows, that doesn't mean these blocks kind of appear sequentially. It's possible that one of these blocks affect what is going to happen in the previous block. For example, this radiative transfer through the intergalactic medium may heat up the gas, and that may start affecting the next generation of galaxy and star formation. So it can be a very nonlinear, complicated process which you have to track throughout. Now, going ahead, suppose you now ask that I want to understand this whole picture and I want to model this theoretically, and I want to do everything in its full glory. So then what you need to do is you have to prepare models which can match different observations. Let's say Lyman alpha absorption and CMB and 21 centimeter, maybe high-redshift galaxies, all simultaneously, because they are all kind of pieces of the same puzzle. Generally, there are various challenges in doing the modeling. For example, you need to probe a wide range of spatial scales along with nonlinear physics. Some of these observations, we are talking about huge length scales. Okay, so few hundreds of megaparsec. So if you are trying to do a simulation, you need a volume that larger size. On the other hand, your simulation should have enough resolution to, for example, identify the smallest halos which probably host the first stars. At the same time, you may need spatial resolution to resolve the gene scale of the baryons. So again, you're talking about extremely high dynamic range, and often this can be challenging. So sometimes people either like compromise on the size of the simulation, or they compromise on resolution and work on some subgrid physics, which is now put by hand. Then there is a radiative transfer, which is a very complex equation to solve. And if you want to solve it fully, it's very difficult to do it numerically. Again, depending on what kind of approximations you do, you can solve it, but the approximations would have to be accounted for. And then this high redshift universe, things are extremely uncertain. So you may be actually parameterizing various of the unknowns. And then there will be many parameters, they will all depend on each other, there will be degeneracies, and it's extremely challenging to explore the full space because you may need to run these simulations again and again with different kind of parameters. And this is again where a lot of effort is being spent, for example, using machine learning to try to see if parameter inference can be made faster. So this has led in the field to different approaches to modeling. At the one end, you have these full numerical simulations. Full meaning they include most of the physics, but they are computationally extremely expensive. So you may need like weeks to months to run one of them. The other extreme is kind of analytical or semi-analytical, where you reduce the whole problem into a set of differential equations coupled, and then you try to solve them. And they are extremely fast. But you will make a lot of approximations for the nonlinear physics. You're not going to do them in the full glory. And there is something in between where, which have become quite popular in recent times. Those are the semi-numerical simulations. These are basically where you do a simulation in very low resolution and then try to approximate much of the nonlinear physics at the subgrid level and try to get things done. So you will get a simulation box, but that is approximate in this case. And here I will be talking about some of these things which we have been doing. One is we have played a lot with analytical models of reionization, and I will show you some results from that aspect. And then I will try to tell you what we get from some semi-numerical simulations of reionization, and let's see how things go. So what we did was we made an analytical model, which we now call it Cosmological and MC. So basically it includes all the cosmological parameters, some of the reionization physics, which have been parameterized using various parameters. And then along with all the cosmological observations, which could be CMB, supernova, or whatever the standard cosmological parameter inference do, you add some of the observations relevant to reionization. This could be quasar absorption systems at the end of reionization, any like measurements of the neutral hydrogen fraction you have at various redshifts and so on. And then you will be having all these cosmological parameters as well as all these parameters related to these galaxies, and you try to constrain them using some kind of a MCMC technique, and you will get various contours like what you get in standard cosmological inference. What we were finding, this was done quite some time back, was that once you put in the reionization constraints, because they come with their own observations and their own parameterization, they put independent kind of narrower constraints on the reionization optical depth. So what has been shown here is a 2D contour plot of tau versus the parameters which define your primordial power spectrum. And as you know, and the green one would be the one you will get if you do a conventional CMB analysis like matching the Planck data. And this degeneracy direction in tau and the normalization of the power spectrum is well known, so this is what you will get. The moment you put in the reionization constraints, what will happen is your tau will get better constraint, and that will essentially make your constraint on AS, the amplitude, tighter. And that may kind of propagate into other cosmological parameters. So this is just to show that in principle there is information in reionization modeling and the corresponding data which can affect your inference on the cosmological parameters. We are still talking about standard lambda CDM here, so no extension or anything to that. Once we saw that, we thought that can we now go ahead and see if we can start asking questions about non-standard extensions to lambda CDM. And one of the things which has become quite interesting is to see that how normal cold dark matter actually will show structures up to extremely small and small scales. Now you can ask that, do these structures wash out at some scale, and can we put some limit on the scale below which the structures don't form? What will happen is if you wash out power at small scales, the first galaxies will kind of form relatively late compared to what you would have thought otherwise. And in principle, these observations can put constraints on that. So one of the models are so-called warm dark matter models, which is like described by a mass of the dark matter particle. And again, I should say that many of these constraints have inherent assumptions on some of the astrophysical parameters. But this is just to show that using current or with future experiments, it is probably in principle possible to put limits on these parameters. And if there is any chance of detecting these, that may also happen, but not now. Sorry? This is the probability distribution of the parameter, of this parameter. Sorry about that. Yeah. Yes. So basically with the present data, what you will get is a kind of upper limit. But then we try to forecast with future data as well. And you will see if it's CDM, then the upper limit will get more and more constrained. Whereas if it is truly a warm dark matter particle, maybe you will be able to detect them. So that was the point of the picture. So this is where the early universe or the high redshift universe studies connect to cosmology, basically. I should also say that this was done a few years back, and we should update it after the JWST results. So things may change. So this is something which we plan to see. So now that I've used the word JWST, I have to tell you how things have changed with JWST. So this is a plot from a review article which is almost 2 years old now. So what has been plotted here is the luminosity versus redshift. Each of these points is a galaxy, spectroscopically confirmed galaxy. The blue points are the galaxies identified pre-JWST. And you will see there are only few tens of them. They are mostly bright, high luminosity, and they hardly go beyond redshift 7 or 8. Orange points are the ones which have been identified after JWST started operating. And now you can see how the field has changed. Firstly, we are going up to higher and higher redshifts. So we are already talking about redshifts beyond 14. We are also talking about galaxies which are much fainter. So there is a wide, there is a huge population of fainter galaxies which were completely missing in the pre-JWST days. I mean, we knew they probably existed, but now the JWST is detecting them. So this is like really changing the high redshift universe field. And JWST is not only just detecting galaxies. Because of the way the instrument works, I mean, you will also get spectra these galaxies, and you may be able to learn much more about these galaxies than what we were able to do during for example, the HST days. Now, once these observations started coming, it also started started surprising us. So what has been plotted in the same paper is a plot of SFR versus redshift. And again, the blue points are the things which were pre-JWST, and the orange points are the one which have come after JWST. Yeah.
So how come they are so consistent with each other even though we are missing so many?
Sorry? Which?
The blue and red points are very consistent with each other even though we are missing so many galaxies in the top panel, you see.
Yes. No, what I was saying is this part. No, but okay. So there are, okay, so firstly what you are plotting is normalized to a volume. So even if you are measuring less galaxies, you will be able to do that. Secondly, when you are plotting SFR, there are assumptions going. In the sense, even though you are not detecting the faint galaxies, you will make some extrapolations. Because SFR is the total star formation rate of the whole universe. So it is not measured only from the galaxies you observe. You make some assumptions about how the faint galaxies behave.
Extrapolations by good extrapolations consistent with what
Yes, yes, yes. I will make this point slightly more like robust, but just take this as a qualitative answer.
Do you have red points at 6 and 7?
Which one?
At lower redshifts or JWST at 7?
Yes, I mean that did not change basically with JWST, yeah.
Why is one of the Hubble Space Telescope star formation rate measurement an upper limit and another one a lower limit?
This could be related to incompleteness and how you have modeled. See, many of these things come from the lens fields. Okay, so this could be. So I cannot comment on individual points, but yeah. But again, just take this plot as a qualitative one. I will make some of these things more quantitative in my later plots. But what I'm trying to say, the takeaway message of this plot is that we had a kind of model of, let us say, constant star forming efficiency, which is shown by this, like this gray line, which we were quite happy with during the pre-JWST days. And now you see, once the JWST data started coming, they were consistently above these lines. So people started then worrying about the fact that definitely we are missing something, which means either our galaxy formation model needs revising, or maybe there is something in the ΛCDM, early structure formation, maybe more halos are forming. And it basically opened some kind of a small Pandora's box, and a lot of discussions happened, and is also happening in the literature, in the community. And I wanted to tell you what is going on. So do we think there is challenge to the ΛCDM model because of this excess? So to modify ΛCDM, there are broadly two ways people have tried. One is people tried to put in, speculate or postulate excess in some matter power spectrum at appropriate scales, at appropriate redshifts. There could be some physical motivation behind that, may not be. But essentially, if you put some excess in the power spectrum, you have more fluctuations, hence more halos at high redshift. So maybe you then start to match those observations without modifying your galaxy formation model, like at least significantly. Other one was to change the background expansion rate of the universe. So you change Hubble parameter in such a way that it leads to a different growth factor, which then leads to an increased abundance of halos because your growth is now more at high redshift. Some of these models were introduced to resolve the so-called Hubble tension, but that is not important. But people felt that maybe some of these models now can give you excess galaxies at high redshifts. However, the point to understand here is that, remember, I mean, there are all these excesses at high redshifts at 12, 13, and so on. But don't forget all these points which were there, and probably they are quite solid in that sense. So if you are coming with a modification in cosmology, you have to be very careful that you put in more power. Now, once you put more power, you probably solve this high redshift part. But then you will be also forming more galaxies at lower redshifts also, because unless you find a way to switch them off exactly at redshift 10 or so. And then that will be a problem for those observations. So once you account for both pre-JWST, that's the HST, and the JWST data, what you will realize is the scope for such models become extremely, extremely limited. Okay? And I think that is the most controversial statement I will make in this talk. Everything else will be smooth. Okay? So this is something we have been trying. I mean, we for example, took a very exotic dark energy cosmology, and we tried to show it quantitatively. So what has been plotted here is the luminosity function. And that is the correct thing to actually plot, because this is directly observable. So as when I said that don't worry about the star formation rate plot, this is what I meant. These are the observations which one should try to match. So what has been plotted here is the abundance of galaxies against the intrinsic luminosity, and the luminosity increases to the left. Okay, so what has been plotted here is the magnitude across different redshifts. So the black points are coming from observations, and these are basically a model. Again, don't worry about the details of the model, but they have something which gives you more abundance of halos at high redshift, with the astrophysical parameters kept free, but we did not allow them to evolve with redshift. So we are saying the galaxy formation happens similarly across this whole range. What you will see is that this model, although it matches the low redshift observations quite well, at high redshift they still fail to get the luminosity function right. Okay, they constantly underpredict. So it is clear that once you have these models and account for the low redshift points, that is this redshift 5 to 10 points, it is very difficult to match the high redshift observations without putting in some evolution in your galaxy formation physics. So that is the takeaway point. Yeah. This is a anti-de Sitter universe with a quintessence model. Okay, so you have a ADS universe. Along with that, there is a phi which is evolving. Okay, so I can talk about that. So with the correct amount of ADS and quintessence potential, you can find models which will give you a lot of, like the D plus or the growth factor will be such that you will produce more galaxies at high redshift. Because
growth of a structure at high redshift.
It increases the growth of structure, preferably at high redshift. What happens is the universe doesn't what happens is the growth is not as fast as lambda CDM. But when you normalize this to the present epoch, what you will find is that the growth factor is higher at higher redshift. That is how they get it. So I'm not trying to defend or anyway support this model, but this is just to make the point that when you make such models, you have to be very careful. That is not to say that no cosmological solutions exist, but if there is a solution, you have to try to fit the full data set.
What about the primordial magnetic field?
Yes.
I'm surprised to say it in the same company.
No, it is not the same company. Okay.
It's not non-standard at all.
So, yes. So what happens is when you put primordial magnetic field, you often put an excess in the power spectrum. Same problem.
It doesn't do.
Yeah, so what will happen is we'll put the excess, you will have more galaxies. Now then what you will do is you will tune your astrophysical parameters to match all these observations.
Firstly, you can't put a bound on it either.
In principle you can. We haven't tried that. Yeah.
See, that would be interesting because there is evidence now from gamma ray observations.
That there is a, yeah. May not be very strong, but in principle you can. I mean, we have tried pre-JWST with Shiv and all, but we can check.
That's right.
Yes, and here you will get an upper limit. Yeah.
So the question is if they can bound it from the top.
Yes, but it may not be very strong. Yeah, I'm fine.
Strong upper limit from the forest,
Yeah.
That's much stronger.
So, of course, to give you a solution, we did try to play with the astrophysical solution, and we have a model for, with parameterized model for forming galaxies and so on. And what has been plotted here is that how various parameters of the model evolve with redshift. So this is a parameter which tells you how efficient is the star formation and how the amount of stars get converted into the UV luminosity which you observe. So that indirectly depends on the initial mass function of the stellar population. And you can see whatever this quantity is, up to about redshift 9 or so, we are happy with something which is constant. This was pre-JWST. With JWST, it really prefers something which increases with redshift. And this is a model which will match the full data. And then we went ahead and tried to model it in slightly more detail. For example, we know with how the star formation time scale evolves with redshift and so on. So we think that the star formation time scale is smaller at high redshift, so it's more bursty, and then it slowly goes to the standard main sequence kind of star formation at lower redshift. And this is how it matches the UV luminosity function. In fact, those evolutions were obtained by matching the luminosity function. And now you see there is no problem in matching the luminosity. This is normal cosmology. So no, yeah, it's Planck-based fit cosmology, no changes there. Okay. And then, of course, we also tried to fit various other, so as I'm saying, JWST is so rich, it gives you a lot of other kind of constraints. So starting from the clustering of galaxies at high redshift to star formation timescales to the stellar mass function. So with all these observations coming, now you can start breaking degeneracies between the model parameters and try to constrain or limit each of them. And that is the hope with more and more data.
But those things, I don't know what they are, but they don't look match, right?
These are upper limits, you will see.
Oh, they're upper.
Yes, yes. But if we, even with that, if we now play a bit with the initial mass function and things like that, it won't be very difficult to match. We didn't explore this. Yeah.
Sorry, so the secret ingredient here is what, the most important ingredient to match this?
Most important ingredient is, first of all, you need these parameters, like the star formation efficiency, the time scale of star formation. You have to allow them to vary with redshift as liberally as you can, because earlier we used to keep them extremely tightly constrained. And that, if the star formation time scale is very small, you may have to introduce things like equivalent of duty cycles. So all galaxies may not be bright at the same time when you are observing, because they have formed stars and maybe they're become quiescent.
Six free functions?
No, we have, so these are, like some of them are derived, okay? So we have about, slightly more than that, 8 free parameters. It's two free functions, but each parameterized by 4. Yeah. Yeah.
In a quick question regarding, so because you are usually always look at luminosity and not stellar mass.
Yes.
So one of the issues which I have with the JWST findings is that how well do we really understand the light to mass ratio conversion?
Yes.
Particularly at these redshifts where the
Yes.
calculations are done in lower.
Yes. So what happens is, so that is why I would not take these points very seriously. We don't use them to fit while doing the fitting. Stellar mass function is always a derived quantity and depends on a lot of assumptions. Okay, so you have to be very careful. You have to input a star formation history. You have to put an initial mass function, everything. Okay, so you have to be very careful. And I agree, we don't understand many of these things together. Ideally, I mean, you will probably forward model. If you have a model for galaxy formation, you forward model everything and see. But matching the luminosity function is always the best thing to do. Yes. And then you don't have to worry about how complete things are at faint end and things like that. Yeah. Yes. So these analytical models, the challenge is you can only predict things which are relatively simple, like globally average quantities, globally average luminosity function, globally average reionization history, some global signal. If you want to study like the spatial variations, you will need to model these fluctuations. And these fluctuations actually probe the properties of the source. And this is a movie which shows that this reionization can very much depend on what kind of sources drove it. If they are faint galaxies, you will see these black regions will be many, but they will be smaller. Whereas if they are driven by rare bright galaxies, there will be a few, but they will be huge. Okay, so the topology will be completely different, and the hope is to get information from these kind of observations. And yeah.
Suppressing galaxy formation because of the proximity effect.
Because of the ionized regions. Okay, so this is a simple visual thing. When we actually do the modeling, I mean, this is just to show you visually what happens.
Nobody even knows the sign of that effect, and that's been the case for, I don't know.
So yeah, agreed. But what we are doing is to self-consistently calculate in our models, self-consistently calculate the temperature of the gas as the universe gets heated up, and then how that affects the gene scale which forms the galaxies.
Is this somehow using excursion sets?
No.
What is it using?
It is using something what we call photon-conserving semi-numerical models. It actually solves.
We won't do it here, but I want to find out all about
Yes, so it solves some of the problems we had with excursion set models, and I think we are very happy with this. Great, yeah. And this is something which we are doing now. The advantage of semi-numerical models is that, I mean, these are low resolution simulations. And for example, you can generate huge boxes and study reionization there. For example, this is a 1 gigaparsec box which we have run. And I mean, without much computing power needed. Okay? And this is like going from redshift 20 to redshift 6, a typical reionization model. Okay? And then what we do is we put in subgrid physics, and I'm not going into the details, but we can find models which match a wide variety of observations. And I won't have time to go into that, so I'm relying on Girish to tell you about some of these observations in his talk. But what we can try is to match various of these observations as much as we can. However, what happens is the price you pay for this, yeah, Arman, you have.
You have so many extra degrees of freedom, right?
Meaning, yeah,
So
we do.
Why should just one line?
Oh, yeah. So this is the kind of best fit model, and that will be my next slide.
What would be the other ones?
Yes, we still don't know the answer. So this is something which is happening now, and I will tell you why. The price we pay for a semi-numerical model like this is the number of free parameters. They often are many more than what we can deal with. Okay, so this model had like 8 parameters for the galaxy formation part and 5, 6 for modeling the intergalactic medium. The moment we do that, parameter inference becomes a challenge. Okay, we cannot do a conventional MCMC, and this is where we need to build something which we called an emulator or an interpolator, and this is where we are spending a lot of time. We have done that for a small subset of these models where we don't vary all the parameters, and it works well. We have found a emulator which gives us something like 100x speed up. But this 14 parameter model is still a challenge. And I can talk about what are the new things we brought in developing this emulator separately. But there is a lot of challenge in even developing an emulator. So machine learning itself has its own challenges, particularly in the high redshift universe modeling. Okay? And in the future, the hope is that with 21 centimeter experiments coming, we will be able to probe properties of this fluctuating hydrogen field quite nicely. And there is a wide variety of probes which are ongoing. These are a representative list of probes which have taken data or taking data which try to probe these 21 centimeter fluctuations at high redshifts. And the future is probably the SK. And as I said, the first target is to get the power spectrum of 21 centimeter fluctuations. It's not an easy probe because the signal is extremely weak and you are overwhelmed by astrophysical foregrounds. So this shows the power spectrum versus redshift for a particular scale, and these are various upper limits from a wide variety of observations. This is where we believe our typical models would be. So we are far away from there. And the challenges these observations or these groups are facing is to deal with the astrophysical foreground. So the limits are not going down as fast as we would like them to go. So this is a very challenging experiment which is coming up. On the theoretical side, we are trying to understand somehow how to account for some of these systematics and then see if we can model them out and try to see what kind of forecasts we will have with the future experiments. And since I talked about SK, let me spend last couple of minutes on the SK, because this is something which has become quite important for me, for India now. So as you know, this SK is the next generation radio astronomy telescope which is coming up. And it's headquartered in the UK. There will be dishes in South Africa and low frequency antenna in Western Australia. SK is happening as we speak, so I don't have to show like artist's impression because the construction has started. So these are real pictures. This is the first slide from SKLO. And India, as you can see, is a full partner of the SKO now. I mean, we have been fully funded by the government of India. The timeline, as you will see here, don't go into the details, but from the first half of 2027, we will start having what we call the science verification data. So the users will start to play with the data from that time, at least from the Australian part, which is interesting from EOR. And by the end of the decade, we will start the cycle 0 observation. So things are actually moving very fast. There is a lot of activity happening within the within India. There is the SK India consortium, which consists of a wide variety of organizations all over India. And the chair currently is Pankaj Jain. I think he was supposed to attend, but he could not travel for this meeting. So we are becoming very much active in the SK front, which also relates to the kind of science I have been talking about. So let me not go through the summary again. So let me thank and take questions if any.
Questions from the audience. Dick, yes.
Can we go back to your grouping of who we're a big block in blue Canada, and
Oh, you mean the SK member countries? Yes.
And we will focus on the India thing as well. You notice how many gray spots there are. And you know, it wasn't clear to me that it's the best expenditure of money, but given that we're in it, we have to exploit it, and as do you. It looks like you're better advanced in that. We've got great radio in Canada that's sort of a new generation with chime and chord.
Yes.
But, I think that you also mentioned,
Hera.
you mentioned the
Hera?
Hyrex,
Hyrex I did not, yeah, but yes.
Sievers thing.
Yeah.
So can you go back to the India-only picture you had and who's engaged? So can we just sort of go through there? What is the level of engagement of all of these places?
Yes. So the most of the effort is being led by NCRA, where I am in. So basically, NCRA is leading both the science efforts as well as whatever we are contributing to the technology part, and that I can talk to you separately what kind of technology we are contributing to. Among the other institutes, IIT Indore, to some extent RRI, I mean, there's hope that they will get involved in the technology development or software
RRI
development
is
a
well
bit.
developed. What about theory in TIFR and Mumbai? Is there any?
Yes, I mean, there are people who are interested, yes. You mean DTP, you mean?
Well, I'm looking at Shubha, but I'm not looking at him. But,
yes. So people are interested there. They are not formally integrated into this picture, but they are. I mean, so this is again a very representative list. Yes, but DA is part of this already.
The previous map, the world map.
Okay, you want me to go back?
I want to object to this map because Canada is shown as bigger than Africa. It isn't.
It's a projection effect. No.
Are you saying we loom large? That is true, but yes, it's a distorted map.
No. They are not. So these are the flags. This one? I hope not. No. They are not part of that. So I don't know how the Chinese map was drawn.
Yeah, because that's covering Kyrgyzstan and Tajikistan.
Okay. That's.
Did you say Mongolia was in?
I hope not.
It's
probably here.
you know,
No, I think it should be reasonably accurate. I mean, they have to be very careful about the political
but this
implications.
is good. So China is, Japan is integrated in?
Yes. Japan is now part of. So there are some differences between people who are full members and people who are observers. So Japan is still an observer. They are on their way to getting integrated. But so Japan, Korea, I mean, hopefully they will become integrated in. This is an official map from the SKO website, and this is what we use.
Hey, last two questions, guys. These are not serious questions. We have two more people here. Sorry.
You can go to prison if
Yes.
you show a map of India without the right borders according to the government.
Yes, okay.
This is
No,
also
this is
a very
approved by
interesting
Indian
map,
government,
actually,
DAE
yes.
as well. Yeah.
Ramesh, the last one belongs to you. Please, you first.
So me first? Okay. So I just want to make sure I understand it. So can you just tell me how much is the star formation rate elevated with respect to the Maddow plot if you assume if you prima facie, if you assume the JWST result.
So as I firstly mentioned, that converting these, suppose you assume that this model is correct or these observations are all fine. Converting this into star formation rate, there are assumptions which go in. So even taking the Maddow-Dickinson plot on its face value, I mean, there could be issues, okay? You have to, where do they put the faintness limit and things like that could be important. Yeah. Low redshift, they're probably fine, but high redshift, there could be issues, okay? Yeah. So I don't have a number for star formation rate. It will very much depend on what I assume at the faint end, basically. So as I'm trying to say, star formation rate is not something which is...
Yeah, but I think you showed a plot of star formation rate versus red, and it was much higher than the gray curve. Maybe I misunderstood that.
So this is a gray curve which was pre-JWST days. Okay. I mean, there could be better models than this.
Anyway, so just the reason I'm trying to ask from a different angle. I mean, superchem you can't just put gadolinium, and the main goal is to detect relic supernova neutrino background, which is extremely sensitive also to the star formation rate. Yes. If this is elevated, then they should also see a signal, I think.
Yes. So we believe star formation rate is elevated. I mean, that is coming from our models as well. But the exact number could depend on how you model the star formation at the faint end. That is my only point. So you have to actually forward model the supernova part as well. It's not a clear number which I can quote. It is elevated, but I can't give you a number whether it is 5 or 10 or how much. Yeah. There is uncertainty.
Last two questions.
You showed two SK antennas, one which is like a pointing dish and another which is like a Christmas tree cone of, maybe dipole antennas. Is one meant to be for low frequency and the other for mid?
Yes. So what will happen is, we will have low frequency antennas in Western Australia, we will call it SK low. Yeah. And then we will have dishes in South Africa, which we will call SK mid.
And the dishes will point while the other ones will be offline beamforming, or is it?
Yeah, you can form offline as well. So you will have stations.
Yes.
And yeah, you will collect data, and the beamforming will be at that, what we call the software level. Yes.
Okay.
Yes. Yeah.
Last question, you had something to ask.
Just a quick comment regarding the supernova one. So there is a delay for the supernova to happen. There's a significant supernova burst to happen. These are at very high redshift. So we are still primarily dominated by the star formation rate at a lower redshift than a redshift 14, because the supernova models, the supernova burst to happen will take few tens of mega years and so.
No, but
yeah, but you add up everything, so you still are dominated by the larger
still talking
number.
about 10 to the 7 to 10 to the 8 years, if you're thinking of
that's right.
high massive
ones. So that's tens of millions of years.
Yeah, but what he's saying is if it is elevated quite significantly, whether they can compete. And
I think that number will be not too large. You know. Yeah. So this, for Maddow-Dickinson star formation rate, there is about a factor of few difference. We have seen this recently in the context of some other studies. So if you compare the JWST integrated star formation rate density.
No, that's what I'm saying. That will depend on what you assume.
Yeah, that's right. Galaxy. So with these assumptions and Maddow-Dickinson assumptions, it looks like not matching very well.
No, Maddow-Dickinson anyway. I'm not bothered about Maddow-Dickinson. What I'm saying is, even at high redshift, even within the models which are allowed by the data, you can see the kind of spread I have at faint end. And depending on which model I take, I can get whatever numbers you want there. So I'm saying there's a lot of uncertainty unless these data points get filled up with future observations. So there's a lot to worry about there.
Go for it.
Yeah, but again, star formation rate, you have to be very careful. No, be very careful. Star formation rate, there is IMF, you have to find out how many massive stars you are forming. So one has to be very careful in quoting these numbers. That's my only point. Yeah, I think I should stop.
No more questions, my veto here. No, please. Okay, fine.
Yeah, but this is without the slides.
I mean, you add 8 parameters for a star formation, and then what if I find a cosmology with 3 or 4 degrees of freedom, and then fit your data at the high redshift? Do you think it's worth exploring it?
It is worth exploring.
Yeah.
See, the thing is, you have to find a cosmological model which does something around redshift 10, non-trivially.
Loitering models?
Huh?
Loitering models?
Possible. I am not I'm not an expert on, but yeah. What I'm saying is the models which have been explored in literature often just concentrated on these high redshift data points, and that could be very risky. Okay. So in principle, yes. I mean, yeah, whenever I give this talk, people have come up with ideas, but yeah.
We'll continue with the theme of reionization with our next speaker, Girish Kulkarni. The title of Girish's talk is From the Last Neutral Islands to the Dark Sector, Reionization as a Lever on Cosmology. Over to you, Girish.
And this is consistent with CMB and other experiments, because that will, sorry.
Use the intervening moments for comments and questions if you want.
Okay, I guess the one thing we have learned in the previous talk is we shouldn't talk too much about galaxies. So I'm going to focus on what is not a galaxy, namely the intergalactic medium. My name is Girish Kulkarni. I don't attend these non-lambda CDM conferences too much, so I'm looking forward to the discussions this week. But that's also why I might not have met many of you. I work in Mumbai at the Tata Institute, and the results I'm going to show are mostly developed by my students and postdocs in Mumbai. What I thought I'll do is I'll try to argue that understanding the IGM is now an important scientific goal for cosmology, and I'll try to demonstrate a few results that we have developed towards that goal in my group. So we usually describe ourselves as people working on cosmic dawn and the epoch of reionization, as Tirth very nicely showed in this, starting from the emergence of the first astrophysical light in the universe until the establishment of the UV background. And sort of the key words in this discussion are the IGM, the intergalactic medium, which is the diffuse baryonic distribution between the galaxies, the emergence of the first stars, which is often referred to by cosmic dawn, as cosmic dawn. I think this term was coined by Aaron Parsons of Hera. And finally, the emergence of a UV background in which you have a all-pervasive distribution of UV light in the universe. And the point at which this happens, we refer to as reionization. And sort of the usual motivation that I give in my talks is that this missing chapter is not only interesting in itself for people like me who are interested in the IGM, it's also a very good constraint on formation of galaxies and black hole. And I think this nicely came out in Tirth's discussion. In this talk, however, I also want to argue that it's also interesting from the point of view of cosmological inference. The IGM contains most of the matter of the universe, which is why we like to study it. But the IGM, as a result of containing majority of the matter content, also affects cosmology, as done using probes like the CMB. So what is happening these days in reionization studies is there are multiple probes that are potentially helping us to go to higher redshift and understanding how reionization happened and how the IGM evolved from the cosmic dawn. But one of the challenges we are facing, as I will argue, is that these inferences are still very fragmented, and there is no clear consensus amongst the community as to how exactly reionization happened. And as a result, taking advantage of this confusion, what has happened from the cosmological angle is that reionization is often caricatured as something extremely simple, which often completely ignores the rich astrophysical information that we now have. And then funny things happen. And so these two plots are a good example of these funny things. This is from a paper by Saylor et al. Very recently, where they, on the left-hand panel, show a model fit to the DESI BAOs and CMB data. And they argue that if the tau, the free electron optical depth ceded by reionization, is increased from the Planck favored value of 0.06 to a value of 0.09, then the preference for an evolving dark energy melts away. Similarly, they also showed that the effect that reionization has on the neutrino masses is also significant. What is shown in this plot is that if you change from a tau of 6% to tau of 9%, the sort of tension that BAO CMB have with the neutrino mass measurement experiments also reduces in significance. And so what I want to argue in this week's discussion is basically we have come to a point where it might be interesting for us to start looking at reionization from a non-CMB angle a bit more. And so let me tell you what that angle looks like at the moment in the evolution of our field. Now, classically, reionization was studied mainly using something called the Lyman alpha forest, where you find a bright object at a cosmological distance and take its spectrum. Typically, you use a quasar. And then what you see is that the intervening IGM produces these features which are referred to as the Lyman alpha forest, and you can use, if you have a high enough resolution on your spectrograph, you can use this to constrain the thermal and ionization state. Now, this is great, and this has been used now for about 2 decades to very precisely measure the IGM structure from redshift 0 to up to redshift 6. But unfortunately, for a variety of non-fundamental reasons, at redshift 6, Lyman alpha forest breaks down. And you can see this breakdown in this famous plot by Javifan already quite a bit of years ago, where you see that at redshift 6, quasars show completely saturated Lyman alpha forest absorption. There are no lines to resolve, and as a result, there is no IGM to be studied. And so at this point, the reionization study is kind of saturated, because all that you can do at that point is produce limits. You can say, well, I have saturated Lyman alpha absorption. I can maybe assume that all of it is neutral, and then that gives me an upper limit on the neutral fraction or a lower limit on the ionized fraction, and then that's it, nothing else. I cannot proceed higher in redshift. In fact, over coffee in about 2016, Javifan told me that since 2006, when he measured those spectra, there was essentially no progress in the 10 years on the problem of reionization. And this changed recently quite a bit. We have now discovered a new way of finding information in the Lyman alpha forest, namely the information in the spatial scatter in Lyman alpha sightlines. And so here is an example of that. Here are 2 Lyman alpha forest sightlines. Both are at redshift 6. The top horizontal axis shows you the redshift. So they are sort of at the same time in the history of the universe. But they have very different structure. In fact, one of the sightlines is extremely saturated, opaque, but the other is extremely transmissive. And you can quantify this in various ways. And when you do that, you get a plot that looks like this. Let me walk you through this. What is shown on the x-axis in the right panel here is something called the effective opacity. You can think of this as the strength of the Lyman alpha forest. If tau effective is high, most of your absorption lines are saturated. And then what is shown here is these cumulative distribution functions of tau effective values at redshifts from about 5 to 6.2 in bins of 0.2. And you can see that as you go to higher and higher redshifts, what is happening is that the distribution of the tau effective is becoming broader. What that means is that the Lyman alpha forest is showing significant scatter on the sky. What you see on the left-hand side here is that the values are also increasing. The mean values are also increasing, which means that the universe is getting more and more opaque. It turned out, very surprisingly, for reasons that need not have held true, that this actually has information about how reionization ended. In fact, when we managed to construct models which fit these distributions of tau effective, what we learned was that this spatial structure in the Lyman alpha forest required reionization to end in a very narrow redshift window around redshift 5.3. This is often not acknowledged in the CMB literature, but we now think we understand the last stages of reionization very, very well because of these spatial scatter in saturated Lyman alpha forest sightlines. It's pretty remarkable, I think. And so I'm not going to go into the details of that because I want to discuss what we have learned in the last few years, particularly after the JWST started throwing amazing discoveries at us. But what I want to summarize here is that the Lyman alpha forest then unexpectedly has yielded a picture which we have thrown a battery of measurements at it, seems to be concordant with a large number of high redshift measurements.
How many such lines of sight do you have for quasar spectrum?
About 30 or 40.
And widely separated?
Yeah. This is growing very fast with Euclid now. We will have many more with Euclid as it discovers new quasars. And so the overall rough picture that is emerging is that the reionization ends at redshift less than 5.5, possibly has a midpoint at redshift 7. And so what I do in my research is I'm now asking if I can extend this understanding to the early stages of reionization. Can we develop the same level of confidence towards the midpoint and the early stages of the reionization? And luckily, JWST has been very timely to ask these questions. And spectacularly, JWST has thrown up a remarkable number of discoveries which we had not expected in the epoch of reionization. There are 3 I'm going to highlight here, and I'll discuss these and what we have learned from these in the next few slides. So the first remarkable discovery, in my opinion, and I have been spending almost all of my research time on this now, is the discovery of special galaxies known as Lyman alpha emitters out to redshift of 13. These galaxies are very interesting because their existence is a clue to the properties of the intergalactic medium between us and the galaxy. So I'll come to this in greater detail soon. Another amazing thing that the JWST has thrown at us is a missing population of faint AGN, which seem to be abundant by more abundant than expectations by a factor of maybe 100. Okay, these are quite faint compared to the classical quasars. However, they are AGN, they have broad lines, and as a result, they have interesting consequences for reionization. And finally, something that Tirth very nicely went into great details of is the fact that there are galaxies out to redshift of almost 14, 15 itself is remarkable, and JWST has now measured the UV luminosity function. And so what I have been doing is, what does all this mean for reionization and cosmic dawn? Indeed, I'm not the only one who is asking questions like this. People have already started interpreting these JWST measurements, and that little plot that I showed a few slides ago already has lots and lots of points, which you can see are gloriously inconsistent with each other. Right? So lots of cleaning work to be done here. And so sort of the grand goal of this area that is emerging, the mission that is emerging, is whether we can build a coherent picture of reionization and cosmic dawn. And for the cosmologists, I would also urge you to pay attention to what JWST is telling us, because it might have, as we saw in the Sailor result, implications for our measurements of cosmological parameters. So in the remaining talk, I'm going to show you a series of results that we have been producing towards this goal. So how do we work towards this? The first thing is we avoid galaxies like plague. We do not want to model galaxies. We do not care understanding galaxies. We don't want to measure their number, nothing. We want to focus on the IGM. So we construct a simulation method in which galaxies only appear as an aggregate phenomenological parameter. It's a parameter that we don't even bother to map to the real observations. It's actually a purely phenomenological single function that is the one free function in these simulations. And then we make use of the fact that we now have great GPUs to solve the radiative transfer equation. Now, once we make these two, once we bring these two insights to the table, the IGM is a very well-posed problem, because we really understand the initial conditions thanks to cosmological structure formation. And then all we have to do is a radiative transfer calculation using GPUs given a free function. And we have used this very well over the last few years, and we have some of the biggest reionization simulations now as a result. And another thing we have learned is how to calibrate these simulations. So we have now learned how to design simulations which reproduce by design the Lyman alpha forest in the post-reionization universe. So here is an example output from one of these simulations. You have seen similar nice light cone plots in Tirth's talk as well. You have the first objects emerging at some high redshift, and then these objects are producing hydrogen ionizing radiation, which carve out these ionizing bubbles, which percolate and produce today's universe with a UV background. Now, one of the interesting problems of this approach is it doesn't have an explicit parameter space. In fact, this is a very serious challenge, and this is something that I'm worrying about at the moment. And so, because you do not have a parameter space, it's not obviously clear how we are going to fit these models to data. I'll show you what is the best we have been able to do. But for the purposes of this talk, one of the ways we are going to actually study reionization in the middle and early stages of the process is by actually constructing simulation models which begin reionization at different redshifts, but still are completely consistent with the post-reionization Lyman alpha forest. This is a very hard exercise. In fact, in about 6 years, we have managed to come up with 7 such models. It's not at all easy to do. The Lyman alpha forest is an extraordinarily strong constraint. And so, for example, here we have a fiducial model which is very late, starts late and ends late. We have an early reionization model and what can be called an extremely early reionization model. And then, similarly, what we could do is we could have a freedom in the source model. Again, we are not going to do galaxy formation. We are only going to count the number of ionizing photons that halos give out, not the UV photons that JWST sees, not the galaxy formation physics that Tirth modeled. But then what we can do is we can play with our source models. So for example, we could say that only high mass halos contribute to reionization, in which we have a model that can be termed oligarchic. We can say that all galaxies contribute equally, in which we can have a model that can be termed democratic, and a more fiducial model where the luminosity scales with mass in some fashion. And remember that these scalings are now redshift independent phenomenological functions, which I get results for when I fit these simulations to the data. What are the kind of things we are learning from this exercise? The first thing we are learning is that the Lyman alpha forest admits a range of reionization scenarios. It is extraordinarily constraining, but it still allows for a significant freedom. And so here is an example of that. This is the mean Lyman alpha forest transmission as a function of redshift. And these 7 models that I'm going to show, shown here, I'm showing only 5 on this slide, are all in agreement with the mean transmission. This is just by hand. This is the calibration plot. And you can see that there is a wide distribution in the evolution of the neutral ionization fraction as a function of redshift. So the fact that there is a range of reionization histories admitted by the Lyman alpha forest is the first thing that we learn. I'll quickly show this one thing. It's probably not that interesting to cosmologists, but we have seen this very interesting phenomenon that the volume averaged ionizing luminosity density as a function of redshift seems to require a feature at around redshift of 7. We don't quite understand this. This seems to be happening in models after models where people have done simulation reionization calculation in completely different ways. I'm happy to talk about this if people are interested in that aspect. But then we can keep going. We can actually model these new AGN that JWST has discovered. Earlier, reionization by AGN used to be considered impossible because there are just not that many. But then now JW has discovered hundreds of AGN, which are pretty faint. And so the question is whether we can have now a reionization model that is in which reionization is completely driven by AGN alone. And so we have managed to construct such models. And the new insight that came out of this is that the AGN contribution can also be constrained by the Lyman alpha forest. And I think this requires greater investigation, but I really like this panel D, where we have shown that if we have an AGN-only reionization scenario, the cumulative distribution functions of the effective opacities are just very different. And this is in a model in which the mean transmission still perfectly agrees with the Lyman alpha forest data. And so this is another example of the rich information content in the Lyman alpha forest. But then what I'm...
Maybe I had asked you before, but I forgot. What happens to the helium reionization QSI-assisted model?
Yeah, so helium reionization constraints are not violated because the helium recombination coefficient happens to be 5 times greater. This is something I learned as well. No, the second ionization doesn't complete.
Second ionization does not complete during
yeah.
this is happening.
Yeah, and the reason is because the recombination coefficient is much greater, so you need a significantly higher number density of AGN for that problem to arise. These AGN are faint.
QSI, okay.
So, yeah, Shubhadeep.
So this was, I was asking questions to you. What about the kinematic scenarios of the result? Because you are now pushing your stuff to a higher shift, and CMB at least SPT has been able to put some bound/measurement.
Yeah.
So how do you just take on that?
No, I think that's a very good direction. I'm open to talking to people. As you know, we have started talking about that in TIFR now. I haven't explored KSZ myself, but definitely it's a very interesting point. As you will see in a second, I'll emphasize it once again.
You earlier mentioned there is no parameter space saying all of these are too complex to be simply parameterized.
Yeah, these are just picked from some parameter space. We are lacking the ability to traverse a well-defined parameter space of these models. These are 7 models we have discovered rather accidentally, which is not.
You should also have like a fractal structure sort of, maybe, do they?
It's not really fractal. It's a very well-known structure. You will see it it will appear much nicer if you zoomed in. These are ionization fronts moving through the cosmic web. It's a very well understood structure. Okay, so what I have been telling you is a few insights sporadically gathered from new JWST data. AGNs are telling us this, and galaxies are telling us that. But then what has got me excited towards the goal of pushing reionization studies to higher redshift is the discovery of these amazing galaxies called Lyman alpha emitters by the JWST. These need not have existed. We are really lucky that we see these galaxies. Nobody could have guaranteed this plot before JWST flew. What this is showing is galaxies from redshift of 4 to almost 14 with redshift on the horizontal axis and the brightness in UV on the vertical axis, seen by the JADE survey on the JWST. There are 2 types of points which do not have an outline and points with black outline. And the points with black outline have this interesting property that they have a very strong Lyman alpha emission line. Now, every galaxy known to mankind has a very strong Lyman alpha emission line intrinsically. In fact, often about 60% of the galaxy's energy output comes through the Lyman alpha emission line. But at these high redshift, we do not expect this line to be visible because the emerging Lyman alpha photons are going to be scattered by the neutral hydrogen between us and the galaxy. And so the existence of Lyman alpha emitting galaxies at high redshift suggests that there is enough ionized region between us and these galaxies. This is information about reionization. Here are some very nice spectra of these. These are 2 record holders, redshift 11 and 13, of these 2 Lyman alpha emitters, and you can see this emission line here and an emission line here. And this has got a lot of attention, and now lots and lots of surveys are being planned, both from the ground and from the JWST, culminating in the Raman Space Telescope, which will actually try to find lots and lots of Lyman alpha emitters in various range of depths and areas. And so what do we do? How do we react to the existence of Lyman alpha emitters? And how can we extract information about reionization from these discoveries? And so the answer to that starts by understanding how the Lyman alpha emission from these galaxies correlates with reionization. And so I like to do that using this plot. What is shown here is a slice from a radiative transfer cosmological simulation where the color tracks the ionized hydrogen fraction. So the yellow regions are completely neutral, and the blue-green regions are completely ionized. And you can see this is, I think, at redshift 7. There are these, most of the stuff is neutral, but there are these small patches which are ionized. Now, all circles here are galaxies, but white circles are galaxies for which, for an observer on the left of the panel, no Lyman alpha is visible. And red circles are galaxies for which, for an observer on the left of the panel, Lyman alpha emission is visible. In other words, red are the galaxies that this observer will term Lyman alpha emitters, and white would be galaxies that will not be called Lyman alpha emitters. And you can see there's very interesting correlation between the redness of the galaxies on this plot and the bubble structure. So the first thing you can see is that often the red points always exist in ionized regions. So the Lyman alpha emission, the Lyman alpha emitterness of galaxies correlates with the location of these galaxies in a large enough ionized region. However, the correlation is interestingly complex. You can see, for example, here, this group of galaxies sits inside a large ionized region, but none of them are Lyman alpha emitters. And what we are seeing here, as a result, is that these Lyman alpha emitter galaxies also respond to the large-scale peculiar velocities in the IGM. If you have peculiar velocities in a certain way, the line is going to be redshifted in the rest frame of the intergalactic hydrogen, and then the damping wing is going to be moved so that the galactic Lyman alpha emission is damped, even in spite of a large enough ionized region. And so what we are learning here is that if a galaxy is showing Lyman alpha emission at high redshifts, it's telling you something interesting about the ionized structure around that galaxy and the peculiar velocity field around that galaxy. So with this understanding, we can now start trying to dig out information from these galaxies, and we can.
This one is from your simulation you're doing.
Yeah.
But that doesn't depend on which set of models.
Yeah, there will be some discussion about the models, but the primary thing would be what is the size of the bubble around the galaxy and how the velocities are around that galaxy. Yeah.
So be a quick question. So about the Poisson lines of size which you have,
Yeah.
and about these JWST outliers of magnitudes.
Yeah.
Are there any of them which are nearby? Can you ask that Lyman alpha fluctuation, flux fluctuation, and the Lyman alpha emitters?
Yeah.
Are there any nearby sources which you can?
Yeah, very good. Yes, yeah. We can have a long discussion. Yes, yeah. You can study correlation between Lyman alpha emitters and the transmission along a quasar sightline.
Was it detected?
Sorry?
Did anyone study this?
It's detected, including by me. Yes, it's detected, and interesting conclusions have been drawn. I thought it was a bit too astrophysicsy for today, so I'm not showing that today. Sorry. But yeah, it's very, very interesting. Okay, so, but with that intuition, maybe we can start discussing a bit about what these JWST Lyman alpha emitters are telling us. So at the very simple level, we can start actually building some intuition by making these plots. So let me walk you through these. What the left panel here is showing is the fraction of the volume of a cosmological simulation occupied by ionized bubbles of a minimum size, okay? So if I fix a minimum size R min, how much of the volume of the cosmological box goes into those bubbles, and as one would expect, this grows as you go down in redshift and as reionization progresses. And then these are the three models that we have been talking about, fiducial early and extremely early. And there are these analogous quantities that we can study, meaning here, for example, what is shown is that if you, alongside the minimum size of the bubble, also fix the minimum halo mass, you can ask what is the fraction of halos above that mass that sit in the bubbles of this minimum size. And again, that also grows in a certain way, a bit more richer information than that. And then a very analogous quantity we can ask is what is done here is fixing the reionization model, but changing the minimum mass of the halo. What this immediately tells us is that if you are to have a galaxy in a large enough ionized bubble at redshift 13, for it to show up as a Lyman alpha emitter, you cannot have a model as late as our fiducial and early models. So you can see from the middle plot or from the left plot that if there is a Lyman alpha emitter here, if there is even one Lyman alpha emitter here, you must have a large number of halos inside big enough bubbles for the Lyman alpha transmission to happen. And so this is what is telling us that these Lyman alpha emitters from reionization are now pulling the start of reionization to higher and higher redshift. So this is where we make this exciting contact with the early stages of reionization for the first time. Now this is very hand wavy. Can we start to make it a bit more quantitative? Before I get into that, this is where we should have the KSZ discussion as well, but this is also where I should point out that if one is to use the language of tensions, the early Lyman alpha emitters requiring early start to reionization then require a tau which is a bit larger than the Planck measurement of tau, and it prefers these new measurements of tau which have been reported, which are a bit larger than the Planck tau. So it's an interesting discussion to have whether this is actually agreeing with these reanalyses of the Planck data favoring the large tau. But in fact, it turned out that the Lyman alpha emitters are much better than just measuring the neutral hydrogen fraction and doing reionization. We can actually use Lyman alpha emitters to go beyond the mean neutral fraction to potentially measure the morphology of reionization. Obviously, that's going to be much greater information than just the mean value. And in fact, this is the major goal of the 21 centimeter experiments like SKA that Tirth told us about. Now, ideally, what one would want to do is imaging, and I'll come to how that might work in a second. But the first step would be to measure the first non-Gaussian statistic, the bispectrum. And so what we have started doing is trying to understand a bit the statistics of Lyman alpha emitters in various reionization models. So these are the 7 models that I have been showing you again and again. And what we have done now is implemented a careful IgM effect on the Lyman alpha, intrinsic Lyman alpha emission from a galaxy, such that we can now model all sorts of Lyman alpha emitter statistics in these reionization model. So for example, the Lyman alpha luminosity function can be derived and compared with data. This is how it looks at redshift 5.7, 6.6, and about 7. There are many interesting things one can say about the behavior of the models in these plots, particularly towards the faint end of the luminosity function. Again, for some reason, this extremely early start to reionization seemed to work well. One could then start to look at the power spectrum of these objects, and this is an example of how the power spectrum evolves in one of these models. And as one might expect, at higher redshift, the power in the Lyman alpha emitter distribution increases, and this is because you have now extremely biased sources forming stars alone. And then we looked at the bispectrum, and this is the bispectrum plotted as the triangle index, and here the same quantity plotted in individual triangle profiles. And it's clear that the bispectrum does have much more information, and perhaps if our estimates are correct, it might even be measurable in upcoming data. And so again, what we are finding is that the bispectrum amplitudes rises with redshift, again, tracing these non-Gaussian statistics. In fact, when we tried to ask which of these two statistics, the power spectra or bispectra, would be more effective in disentangling reionization models, we did a simple reduced chi-square comparison between them. The bispectrum is often the more favored thing. And this is actually another comment which is worth making, which is that there is a CMB hangover in our community where, because we are so used to the Gaussian fields, the first thing we do, of course, is to calculate the power spectra, and often there is value in doing the next bit of it. And in fact, we were so excited about the value in doing the next higher order. Yeah. Yeah, we could start having those discussions, that's right, yeah. We then started asking if we could do some sort of a field level inference, where instead of targeting only specific endpoint functions, what if we sort of meet this challenge of inferring the ionization tomography directly? And we spent a long time on this, and we have managed to come up with a machine learning architecture based on the classical UNet architecture, which seems to do that. And so the early indications are very interesting, and we have now started exploring this a bit to see whether this really works on real data. And here the idea is the architecture reads in a catalog of Lyman alpha emitters and non-Lyman alpha emitters, and then it gives you a map of the ionization or neutral field. And this does seem to work. And so here is an example. This would be comparable to some of the deepest JWST surveys. This size of the field is roughly similar to the Cosmos Webb survey, where what we have included is Lyman alpha emitters brighter than 10 to the 41 ergs per second, and non-Lyman alpha emitters brighter than UV magnitude of -18. This is how that distribution might look like in a mock catalog. And this is the true ionization field distribution, and this is the predicted distribution by the architecture. If we ask how much this worsens if we reduce the depth of the survey, this is the kind of surveys you currently have. This is comparable to the Cosmos 3D survey. Now you can see the number of galaxies is reduced quite a bit. I'll quantify the comparison between these two, but I just wanted to give you a visual feel. And you can see again that it does a reasonable job of actually predicting. The true field comes from a radiative transfer simulation, right? In fact, finally, we started going a bit wild, and we said, okay, what if we only had a survey which produces Lyman alpha emitters, which doesn't have a UV galaxy measurement at all? So this is comparable to the Subaru Silver Rush survey, for example, at about 10 to the 42 ergs per second limit. So you can see there are no red points now, it's just open circles, and it appears that it still does a reasonably good job. It doesn't do a perfect job, but this is how the predicted versus true plots for the XH1 look like in these three scenarios, with the dashed curve being the unit line. What you can see is that you have a reasonably high fidelity between the predicted value and the true value. The performance worsens towards the extreme ranges of the XH1 distribution and towards very small and very large scales. And so the galaxies seem to have information only in some range of XH1 and spatial scale values. We can discuss a bit more about this. I'll move on quickly because I need to wind up. An interesting byproduct of this is it also seems to be able to infer the power spectrum of the XH1 field and the PDF. I think if you have worked on 21 centimeter modeling, it's really thrilling that this is possible without 21 centimeter. We had not expected anywhere close to this to be possible before SKA turns on. Again, these are mock data. It remains to be seen whether Subaru and JWST data will give us equal quality results. But we now have those data. We have run really interesting programs on the JWST, and we are working hard to run these models on that.
Same XH1, did you try to play with different topologies?
Yeah, we have done that. Yeah, the paper is going to be out next week. So.
This accounts for.
Yeah, in fact, we also did randomizing in redshifts to construct really bad surveys and so on. Please talk to me for more details. The point is not to get into the details here. The point is to tell you how we are thinking about the early stages of reionization in the era of JWST. I'll make a contact with 21 centimeter and then end. We have heard 21 centimeter cosmology from Tirth. I'm sure we are going to hear more from others. I wanted to make 3 points which are not often made and then see how you react to those. One is, there is one interesting 21 centimeter observable which is somehow overlooked. The classical 21 centimeter observation which Tirth described uses the CMB as the backlight. And what you are trying to measure are CMB spectral distortion caused by the IGM. But there are radio loud quasars as well. And the advantage of exploring radio loud quasars is that they are very bright, much brighter than the CMB. So they don't suffer from the same severity of foreground contamination as the CMB. So it's a much cleaner experiment. And this is not a new idea. Chris Carrilli first proposed this back in, I think, 2001 or 2002. The point was, and the reason people forgot about this, was that when Chris Carrilli proposed this, there were no radio loud quasars at high redshifts. And this is how this signal would look like if you looked at a radio loud quasar spectrum at about 2 to 5 millijansky noise residual level. You will see these sharp absorption lines produced by the IGM in 21 centimeter. Now, what I like to emphasize about this is that this is a unique probe of the neutral parts of the universe. Everything that I said until now, all of JWST astronomy only accesses the ionized regions. It's only 21 centimeter that can probe the regions which can potentially be on the adiabatic floor. So as we have shown in a couple papers, if you have some dark matter annihilation, decay type situation, these measurements are extraordinarily severe constraints, right? What you are seeing is a very sensitive thermometer of the adiabatic evolution of the universe. But now what has happened is that the number of radio loud quasars have increased by a large factor in the last 3 to 4 years. I think the number is, my postdoc Tomasz Soltyński maintains a live list on his website. The number is about 40 at the moment. Many of them are northern hemisphere. And until the SKA comes, the best telescope is the UGMRT. So we are planning to submit a proposal in January. But if you do get even a non-detection, it's going to produce the first very strong limits on the temperature of the neutral parts of the reionization towards its end stages. And we have now developed interesting noise mitigation techniques which further reduce the telescope time requirements by a large factor. That's point number one. The second point is that Tirth very nicely described this main effort, which is going to be the 21 centimeter intensity mapping of the high redshift universe using the SKA. You get stuff like reionization and so on. But there is a concomitant effort of detecting the sky averaged signal of 21 centimeter. And RRI is, of course, the best place in India to discuss it, given that Saurabh, Mayuri, and others are doing amazing work using the Saras and its sister experiment here. These are their results. All of you must have heard of the sensational Edges paper some time back. What I wanted to highlight here in this conference was that this is as well quite often forgotten as a very powerful constraint on many physics models. And then the null and non-null detections both are very information rich. And they are so information rich that you are then required to come up with new methods to actually infer information from that. So we have developed some methods that I really like, which are model agnostics and which can for the first time connect these radio efforts with JWST efforts. We often forget that these two telescopes are seeing the same objects essentially in very different ways. One through its effect on the IGM, and the other directly in the UV and optical. And then if you have strong low redshift model dependence in the interpretation of this signal, that's not good. And this is what our methods address. Please talk to me more, but I wanted to encourage a discussion between those two channels in this conference. So I guess I wanted to say that there is a burst of progress in our understanding of reionization. So when you use a reionization model in your papers, please consider some of these astrophysical constraints. And then I think what I would like to think about is that it's finally coming together, and I think we have tools now that didn't exist 5 years ago, thanks to JWST and GPUs. So I think there is a lot to be discussed in this space. Okay, I'll stop here. Sorry, I got a bit over.
Questions from the audience?
Just a comment in the context of the CMB hangover that you mentioned. I think it's also worth paying attention to your cousins from the low redshift large-scale structure community, where the bispectrum has been a long-standing probe. I think one of the main challenges in using it for any kind of inference, cosmological as well as astrophysical, has been the characterization of its errors. And if you look at the way Euclid and the other big surveys are now functioning, we are in the regime of thousands of mock catalogs, right? So, and these are these have to be semi-realistic catalogs of what the covariance of your observable is going to be. I am not aware of too many such efforts in the reionization community, apart from Andre Messinger maybe, and maybe Tirth with Script is thinking of something. I don't know whether you have also considered this or not.
No, yeah, I think that's a totally valid comment. Yeah, thanks.
Hi, Girish. Very nice talk. It's a comment regarding the CMB part. So CMB optical depth tau is more average quantity, all sky.
Yeah. And
if I'm not too wrong, it's mainly coming from the constraint from CL, the E mode polarization measured by Planck at low L.
Yeah.
And the stuff which you are talking about are more sporadic high redshift sources. So why a reionization scenario? Because we know that the reionization will be driven by a few outliers to start the process.
Yeah.
So why I can't have a scenario that the global average tau is still at a smaller value of 0.06 as seen by Planck, allowing for a few sporadic loud sources going up to pretty high Z. So I do not see how why a large tau is absolutely necessary given the fact it's a global average, global sky average. I mean.
Yeah, I think you probably have a point there. I mean, in some sense, this comes back to the comment I made that we haven't traversed the parameter space here. So there could be models which behave exactly the way you are saying, but I haven't seen that behavior yet. But I think it's an interesting way to think about it.
Because it's too patchy.
Yeah.
The average and it's too very patchy scenario. So I would say I do not understand to really fold these two together. Maybe you need more data
I guess
points.
maybe one partial answer or a pointer to an answer that I can say is that there are some plausibility constraints on how the ionizing photon number density evolves. And so the patchiness kind of, if it starts early, it's very difficult to keep it constrained to small bubbles for long enough. But again, there might be models which kind of contrive to get that right. But that's kind of roughly the way I would think about this.
So Girish, about this parameter space traversing, see, when you start the simulation, you are probably changing some parameters, right, every time. So why aren't you saying, I mean,
yeah, so I think,
the point you are
I think maybe, okay, this could be a longer discussion, but I'll make a brief comment, which is the simulation, of course, has some parameters. At the very least, it has the cosmological parameters. But it's not clear, but it doesn't have a reionization parameters, because what is being done, apart from the ionizing photon luminosity function. Right? That function is being supplied by hand, and then there is no freedom in the simulation. It just has an IGM distribution given by the cosmology, and then the radiative transfer does what radiative transfer does. The problem with this I guess my comment was, A, this is suboptimal because we can't understand how to produce models that may do things like Shubhadeep wanted. But a second thing is, it's not clear then how to compare these models with efforts such as yours. It's not clear to me whether the RMFP in a semi-numerical model, for example, is something in these models, right? Whereas for you, it is a parameter that has a specific values. It might not have a physical interpretation in terms of an observable. And so we are in a situation where the semi-numerical model lives in a parameter space, but these parameters have no meaning in a full numerical simulation land. This is what I wanted to highlight. I literally have no way to smoothly move in some parameter space in this setup. But again, this is a long discussion, and I welcome any further thoughts if you have.
I wanted to dive a little bit into the radiative transfer that you're doing. You're using an M1 approximation, which means you've got a variable Eddington approximation in which you've gone from Fij equals a third delta ij to 1 k hat I, k hat j. How do you actually implement that in your simulations? I mean, is it really full M1 radiative transport, or are you doing it in an approximate way? I didn't understand that part.
Yeah, so this is also potentially a very interesting discussion to have. The short answer is this is exact M1, where the M1 pressure tensor, M1 Eddington tensor has been used. The M1 has a property which is different from the variable Eddington tensor. So the M1 has a slightly different structure than the optically thin variable. OTVET is something that you might be familiar with.
You're closing off at M1. That means that it's a flux limited?
Exactly, that's right.
Oh, so you have what's the flux limiter you use?
So this is being done at, so these are full speed of light simulations done using the exact M1 pressure tensor. So there is no flux limit. You are using the exact value of the pressure tensor calculated at each point. And the advantage of using the M1 is that the pressure tensor is then local. So the way it's done is you calculated the photon number density exactly at each point and the photon flux exactly at each point. And a combination of those two is what is used as the pressure tensor. Does that make sense?
Well, I don't understand why that's different than variable Eddington.
It's just a different form.
No, it's the same.
No, M1 and variable Eddington have different
Variable
forms.
Eddington is keeping the M2, but with that constitutive relation.
We can discuss more.
Yeah,
It has slightly different forms. But M1 is a rich discussion to have because M1 does have other issues, but we can discuss more about this.
More questions from the audience? If not, we move to our last speaker of the session, Saurabh Singh. Saurabh will tell us about 21 centimeter constraints on the high-redshift universe.
Okay, so I'm the only one between you and coffee, so I'll not try to overshoot. So I'll be talking more on a focused aspect of what we heard in the last two talks, and that deals with particularly 21 centimeter constraints and what we have been able to learn at, well, high redshift is definition dependent, but we are talking about redshift between 30 and 6 here. And I think this is a very timely conversation to have simply because most of the progress that you will see here in terms of astrophysical constraints and other things have mostly been done in last 5 years. So we are now finally inching to sensitivities with this observable where we can put meaningful constraints. So there are different ways to measure 21 centimeter radiation as
Tirth and Girish both mentioned. And I think people do have their favorites on what has more information. But just from a purely observational perspective, if this is my light cone running over this huge range of redshifts, the easiest things to measure are just the mean and the variance. So the mean signal here is what I would be calling as the global signal, and different redshifts mapping onto different frequencies here. So the global signal, the beauty of this is it doesn't need a lot of large-scale instrumentation. A very well-calibrated telescope with just a single element is all you need. This is in spirit very similar to the black body measurement of CMB itself. And of course, fluctuations do contain more information, what I would be calling as the powered spectrum in K-space. Of course, this is as a function of K and redshift both. And in the later parts of my talk, I'll be showing some limits on both these aspects. Having said that, of course, our ultimate goal is to be able to image this directly. But I'm personally very skeptical whether we'll be able to do that anytime in the near future. So I'll just focus on the global signal and the power spectrum. Of course, the story goes back several decades ago. The earliest work I could find out was the 77 paper, which talked about the 21 centimeter radiation from the dark ages. This is before the galaxies formed. But as an experiment, I think things only geared up around late 90s to early 2000s. And I always keep coming back to Martin Rees in his 1997 paper, which has this very promising optimistic line that it is not necessarily unfeasible to distinguish 21 centimeter from everything else. And just a couple of years later, we had the first paper by Peter Shaver that asked this question, can reionization actually be detected against CMB as a global signature? So we are talking about a community of experiments that started roughly around 2000, so 25 years. And what one of my collaborators, Renan Barkana, calls, we are in a pre-Kobe era, where we really don't have a detection that is credible, but we do have interesting upper limits. And the reason is not very far to seek. I think this is a recurring challenge in different faint cosmological signal experiments. So what we are trying to detect is this redshifted signal between 30 and 6. What we measure, this is one of measurements from our own instrument in a place that is 80 kilometers away from here, Gauri Bidnur. And what you see is a nice baseline shape, which is nothing but the galactic foregrounds, which are at these frequencies dominated by synchrotron emission. On top of that, you see all these vertical spikes, what we would call as the radio frequency interference. And right in this band where we expect the signal to lie, we have huge FM contamination from here and a lot of low frequency mark that we probably don't even understand. Buried somewhere there, you have the thermal noise, which at least we have some control over, thanks to integration. But on top of that, there is a lot of instrumental systematics. So if you ask me that what has taken experiments 25 years to get to where we are, I would say the instrumental systematics particularly have been the bottlenecks. It's not the integration time, just a rough order of magnitude calculation will tell you that a global signal can be detected in roughly 100 hours and power spectrum probably in 1,000 hours. And given we started in 2000, we are long due. So it's really the calibration systematics that have caused the bottleneck, and most of the efforts, therefore, you will see are geared towards getting those down. So before I dive into the results, just one quick slide on what kind of systematics I'm talking about. And I personally like to classify that in direction-dependent and independent measurements. Direction-dependent is very similar to probably what was discussed in the CMB context of non-circular beams and other things. Here we call them primary beams, which change very rapidly with frequency for most of the experiments. And what they end up doing is a flat spectrum source, for example, which is foregrounds, can be observed as having a shape that actually can resemble a lot like what the 21 centimeter signal would look like. And this is one of the hardest challenges because that's something you cannot definitively calibrate. You are losing information in the process when you go from the theta phi nu dependent beam patterns all the way to just a spectral profile. You also then have a lot of direction independent effects that deals with your own multiplicative bandpass and additives, which at least we have a better control compared to the next one. And most of the efforts that different experiments have been making is to be able to either calibrate for it or design instruments in a way where these effects are subdominant compared to the 21 centimeter signal, which is roughly at tens to hundreds of millikelvin. On the 21 centimeter modeling side, I don't think we need introduction. We have had excellent talks before me. This is just one of the new semi-numerical setups that I'll be using in my work. This is 21 centimeter space now, but it started back in 2017-18. where we parameterize the astrophysics with these sets of galaxy parameters, so we are still not at IGM. And given our sheer lack of knowledge for these, and particularly how they behave at high redshifts, you can see the bounds go all the way. And most importantly, at least with the limits that we have, I'll mostly be focusing on what I call FX, that controls the extra luminosity of the very early universe, and a bit upon what we call as the background radiation. So if you start just literally changing and sampling this astrophysical parameter space and start translating them to the respective global signals and power spectrum, what you find is, unlike the most traditional way of cosmology where you're looking for one specific signature given a cosmological model, there is fair amount of uncertainty simply because of astrophysics. So even with lambda CDM, we are not looking for one specific signal, but a huge range of models depending on what kind of astrophysics you put in. So the left side basically shows the global signal, the brightness temperature in millikelvin as a function of frequency, which we are tracing as cosmological redshifts. And on the right, what you are seeing is the power spectrum. Yeah.
Those set of blue curves, do you obtain them by continuously varying some parameter, or are these a set of random samples?
You sample it from these bounds of astrophysical parameters. So for each selection, you have a signal.
Okay, so it's some grid in
Yeah.
this n-dimensional field.
Yeah, yeah. So this is again based on what Girish and Tirth had mentioned. This is an emulator-based setup where you train a model, and then basically for any combination of these astrophysical setup, you should be able to get your signal. Right. The power spectrum, on the other hand, is two-dimensional. So not just as a function of redshift, which it evolves over, it also evolves over different spatial scales. So here I'm looking at one specific spatial scale as a function of redshift. But the take-home message here is, unlike cosmological signals from early universe, we are kind of entangled between the messy astrophysics and a fundamental cosmology. So at this point, most of the limits that come from, it allows us to constrain astrophysics, but not necessarily cosmology. So for all practical purposes in my results, I'll be sticking to the Planck 2018 cosmology and only talk about the astrophysics, which is listed here. All right, so I have divided this discussion in 3 different sections. First is measurement of power spectrum itself, and Tirth mentioned about HERA, LOFAR, SKA. So I'm involved in HERA collaboration, and we had some bunch of upper limits recently, and I'll be talking about that, followed by some in-house efforts at RRI for the global 21 centimeter experiments. And finally, unfortunately, I did not see any talk on using 21 centimeter at low redshift, and experiments like CHIME and CORD are really the pioneers in that. So I'll spend a couple of slides at the end to talk about those experiments as well. So for 21 centimeter power spectrum, we do have a bunch of different interferometers. As a matter of fact, the first upper limits on the power spectrum came from GMRT back in early 2000s. HERA collaboration, on the other hand, this is located in South Africa, in Karoo Desert, led by US, UCB, with collaborators worldwide, including here. So this is an array of dishes, and each dish is 14 meters. It's rather cheap experiment in the way this is constructed. And the key here in this experiment is the redundancy. That is, you have multiple copies of the same baseline measuring the same mode on the sky. And this really helps us in calibrating the instrument more. So all these experiments can actually be broadly classified in the way they are calibrated. So some use exact sky models and basically solve for the gains, but experiments like HERA, which are compact, which are redundant, also rely on the instrumental architecture. So long story short, back in 2023, we had the first upper limits on the power spectrum. This is looking at a very specific redshift, 7.9, and a specific region on the sky. So that's another analysis choice that we have. Because the foregrounds, of course, is spatially dependent, we can find out a field that is relatively quiet and only look there. This is k-parallel, k-perpendicular modes. Of course, we assume isotropy, and we do a spherical averaging of this power spectrum to get here. And as you can imagine, most of the low K modes, both in perpendicular and parallel directions, have very high measurements, and these are mostly sourced from foregrounds. For an experiment like HERA, we make sure that the foregrounds are contained in the very low K modes, and all we do is simply avoid them and not make any efforts to subtract. So most of our limits come from much higher regions of K space, which are what we call as the EOR window, where we expect at least that we are dominated mostly by thermal noise and the 21 centimeter powered spectrum. So that's what's shown here, and that's why the low K modes are missing. The black dashed line is the thermal noise sensitivity, and what we have is the measurement as a function of K. So this itself helps us put fairly good limits on some of the non-standard models of the power spectrum. And most of these measurements, as a matter of fact, are limited by noise and therefore would benefit from a very high integration time. So one of the things that we have been able to constrain with these power spectrum measurements is the X-ray luminosity of these sources. And the simple reason for that is if I go back to the power spectrum or the global signal, we are measuring the gas temperature for most of these redshifts as seen against a backlight of CMB. And what Girish mentioned, it's like a thermometer. So for any reasons, the gas is very cold or the background is very high, we should be able to generate signals that are much deeper than what we are seeing here. So that's exactly what we have done with these kinds of upper limits in HERA, which is you look at the radio background and assume that your radio background is not just sourced by your CMB, but a uniform or a non-uniform radio field, which is sourced by mini quasars or galaxies or whatever you feel like. That is this axis. And the x-axis is the X-ray efficiency of these sources. So in local universe, we do have a relation between the bolometric X-ray luminosity and SFR. We since don't know what that evolves to at high redshift. That's pretty much a free parameter. So essentially, what you are sensitive to is very low values of X-ray luminosity because your gas is going to be very cold, and a rather high value of your excess radio, so that the difference between your gas temperature and the background is enhanced. So the region that is excluded by HERA just based on these limits lies somewhere here. As a matter of fact, there are other observations, and I'll keep coming back to that in the global 21 centimeter context, that also help put constraints on these from the local universe measurement. And one can then translate these constraints on X-ray luminosity all the way to the LX or the bolometric luminosity of the early universe high mass X-ray binaries. So this is the posterior that we get. We are ruling out the X-ray binaries that have very low bolometric luminosities. And as a matter of fact, the peak of the posterior kind of agrees well with what we would expect from a low metallicity environment of HMXPs. And mind it, this is just from a non-detection with a rather sensitive upper limit at 7.9 redshift. So we only gain when we go to much longer spans in redshift axis. So this was 2023. Since then, we have changed our feeds so that it goes to much wider range of frequencies. So these new Vivaldi feeds that you see here in the dishes, they go all the way down to 50 megahertz, and that brings the redshift coverage all the way to 29. The first season of observation is already complete, and we have a few hundreds of good nights. But just to get started, we took the first 14 nights and started analyzing that, the results of which have come just a couple of months ago. And again, not going into the details, now instead of just 2 redshifts, we have upper limits on redshifts as high as 24. And this is in some way a landscape globally where we have put limits from other experiment that includes MWA, LOFAR, now NENUFAR, the predecessors like PAPER and even GMRT results. And of course, at the highest redshift, HERA probably is very unique that way. At low redshift, it has a lot of complementarity with other upper limits, but collectively, yeah?
So these are all just instrument noise, what you're showing here? Error bars.
Yeah, so the error bars that go down are limited by thermal noise. The ones you have error bars on both sides, they are limited by some systematic in the instrument.
So when essentially you were saying that you're now very much systematically limited, does that apply to this as well? Or?
Yeah, so most of the K bins are indeed limited just by the noise. So we do gain by averaging more. But some K bins, as you can see here, for example, around 0.7, they are not noise limited. So they may just stay like that unless we come up with a way to model them independently. Yeah. Yeah, so with these multi-redshift upper limits that we have, and most of them being consistent with noise, we can do much more in terms of theory modeling. And mind it, this is just 14 nights of data. And we are going to unleash this analysis methods on some hundreds of nights and see where we go. But just a quick snapshot of what is possible just with this. We have taken a bunch of models, and I really don't have time to get into details. But the broad flavor here is we can assume models where the radio background is just sourced by CMB. And my kinetic temperature is mostly adiabatic cooling with some X-ray heating. But then one can then look at mini-halo contributions so that there is an excess radio background. You can also look at milli-charged dark matter, which can, in principle, bring adiabatic temperatures to much lower values. And what you are seeing is here as the polygons are the upper limits. So at lower redshifts, it has already started to rule out many of these scenarios. So the lightmost color is the prior, then it's 1 sigma and 2 sigma limits of these constraints that we have put just based on upper limits from Hera phase 1 and phase 2. So with that, I'll switch gears and go to the other measurable from the same redshift, which is the global signal. And this is where a lot of in-house activity at RRI comes in. So we have experiments really all over the world, and every conference that I attend on this, I need to add one more line here. And this is really very comforting because all of these experiments, as you can see, do have a very different way of design and calibrating it. So it only adds confidence that if we see multiple, through multiple experiments, if we see the same observations, it just lends more credibility. So I'll be mostly talking about SPHEREx experiment, which is in-house designed and developed here at RRI. It has its own series of evolution right from 2010. It started by Ravi here at RRI, and since then it has undergone different stages of evolution. But then before I dive into that, I do want to give a big shout out of the next venture in this global 21 centimeter field, which is the space-based experiments. So there is a huge effort, I would say internationally, from the US. The DARE experiment was one of the first. Now we have DAPPER, we have far-side proposals. As a matter of fact, NCLE that flew aboard Changi 4 is already in the orbit around the moon. And then here again at RRI, we have a project called Pratush, and I'll be talking about it in a little detail later. That again tries to look at the global 21 centimeter signal from cosmic dawn. And we also have another experiment from India called SEAMS that wants to look at much lower frequencies, mostly to focus on dark ages and other foreground sciences. So there is a very rich set of experiments, both ground-based as well as the space-based. Particularly for RRI, I'm of course giving the talk, but I do want to give a big shout out to the fabulous team. Many of them are sitting right here. Very nice interface between engineering, between science, between algorithm development, and a lot of supports from the other facilities, including our electronics engineering group, mechanical engineering services, and not last but not the least, the observatories that we keep going to for our observations. Okay, so with that, I'll directly jump into the results. So this is now a few years ago when we looked at SPHEREx-2 that was operating in 100 to 200 megahertz right here. Not very far from here, just 150 kilometers, we happened to find a radio quiet location. What you're seeing here is the colored signals have been rejected by these observations. As you know, we still, as of now, don't have a credible detection, so we mostly look at what parameter space is ruled out. And just based on these rejections, one can convert that into a parameter space of, again, extra luminosity, and to some extent the rate of reionization. And we would...
Does this rule out the edges?
No, I'll get to that. So this is a different frequency range altogether. This observation was 100 to 200 megahertz. But yes, just around that same time, when we had got these results, we did have the edges experiment claiming the detection. And most of the people in the audience would be familiar with this detection center at 78 megahertz. And so coming back to your question, this is how it contrasts with the more standard models, which includes the astrophysics that I had discussed earlier. So even as of today, not a single model in the standard cosmology can explain this. That was what led us to develop SPHEREx-3. So from 100 to 200 megahertz, we went back to 50 to 100 megahertz and developed basically SPHEREx-3, these two additions. And with that, we were able to have a measurement of the foregrounds exactly in that range. Of course, we were limited by FM, so we had to cut down at 85 megahertz. And what we found was no evidence of the flattened Gaussian that was seen by the edges experiment. And again, just to contrast, this is what we are looking for in the data, which is mostly dominated by foregrounds. Once we have a description for what the foreground should be, we don't really have any evidence of this flattened profile here. So, yeah. But then the point is we come back to the square one, which is if not this, then really we don't have a detection. But we went ahead and asked this question, even with this data that we have, it has a sensitivity of around 200 millikelvin. We should be able to say a little more than just edges. So we went back to the more not so standard models, but theoretically plausible models that had a high component of radio background. And we tried to combine both SERES-3 and SERES-2, SERES-2 operating at 100 to 200 megahertz, therefore covering lower redshifts, and SERES-3 covering higher redshifts. And the colors are kind of all over the place, but the lighter colors are basically the priors that we get from the local universe measurements. And the darker colors are what is remaining after we put our data for both SERES-3 and SERES-2. So we are down to a parameter space that we can quantify here. This was the work that we did with Harry Bevins and team there, where we were able to constrain bits of radio luminosity as well as X-ray luminosity at redshifts of around 20 to 25. Of course, we don't assume any redshift evolution. We assume constant values across this band. But with this, the question really is, in the era that we have so many other measurements with, and that is something which has been multiple times highlighted by both Tirth and Girish, can we do better than just looking at the global signal or just looking at the power spectrum? And therefore, since we had limits from both SERES and from HERA experiment, we asked this question, can we combine them? And can synergy help us better? And then the question was, why just stop at these two? So we tried looking at other observables that we could look at. So HERA, of course, has these two different redshift bins, and as a function of k, we have upper limits. SERES-3 ranges right from 16 all the way to 24. But then we had measurements from Chandra that looked at unresolved X-ray background, which is an upper limit for us when we are trying to propagate the X-rays from early universe. And then from very low frequencies, we had measurements from ARCADE and LWA that looked at what we call as the excess radio background. It's still a very questionable assumption, but the idea is that even if you account for your foregrounds in the local universe, you are left with something which still is an open question. So our idea was to basically use these as constraints, and therefore, when you do your parameter estimations for astrophysics, you also make sure that they don't violate the local universe constraints on both unresolved X-rays, unresolved radio, and of course tally well with the power spectrum and the global signal. And I just want to give one example. We have constraints on other parameters as well, where the synergy between these experiments actually help you narrow them down better. So with experiments like HERA and SERES that are only looking at the 21 centimeter, they are more sensitive to ruling out cold gas scenarios. So in some way, they are better at ruling out X-ray luminosities that are very low. And therefore, the posterior here really rules down very low values of Lx. But then, if you have very high values of X-ray luminosities, you are at some point going to violate these Chandra constraints and LWA constraints. So instead of getting a limit, you now get a full-on posterior, and with the two observables coming together and narrowing down the luminosities of your X-ray sources. Just this year, we took this work to yet another observable, and I think at this point, none EOR talks can end without JWST. So Jiten and group, we all looked at the luminosity functions that we have from JWST, combining with Hubble luminosity functions at slightly lower redshift. And the idea was that along with all these observations that we have, we can also look at combinations of the UV luminosity functions with these. And the beauty of this is, again, they approach your parameters from very different directions. So most of these experiments before this would tend to put a limit on the maximum amplitude of the 21 centimeter signal that you can have. But with JWST, the beauty is it attacks it from the other side. That is, you can't have a zero amplitude. Otherwise, it simply does not go well with the luminosity functions that you expect. So with these kinds of constraints, not only do we have a constraint on the upper limit, which is roughly 250 millikelvin that as we have known before without any exotic physics, but now we have a lower limit of at least higher than around minus 70 to 80 millikelvins. And at the same time, given the redshift dependence of these luminosity functions that Tirth showed, we should be also able to constrain at what frequencies the absorption dip lies. Because mind it, this absorption is when the X-ray heating turns on and the signal starts to go back towards the emission. So, but of course, these should be taken with a high pinch of salt, I think, because these are very model dependent, as Tirth also mentioned. There is a lot of assumption that has gone into modeling these, particularly the way you would convert your UVLF to your star formation efficiency and also look at their redshift dependence. So with those caveats, this is more of a demonstration that when you combine these multiple observations, you do way better than each of them, whether it's Hera, whether it's Saras, or a combination of this. So now you have a narrower range where you should be actively looking for the global 21 centimeter signal, and clearly it has implications for the power spectrum as well. How much time do I have? Okay, thanks. So what's the next now? So of course these can go on, but now the other mission mode is to be doing better in terms of instrument design, in terms of observations. So we have also in the last couple of years explored better locations, because RFI continues to be a big player in how much science we can do with the data. And as a matter of fact, the same location where we had results like these is no longer usable. The situation is very dynamic, and that's a common story across different experiments. So we have looked at places like Andaman Islands in India, Ladakh, and a couple of years ago we also looked at some regions in the Arctic, which have been found to be very useful, at least for some frequencies. Recently had a nice paper led by Yash, who is in the audience here. So we are now planning to do a bunch of newer deployments with a better system, because each analysis also gives you some knowledge of how you can do better in terms of your instrument design. So Saras 4 is already in. This is a nice picture someone took from our team just in front of our main building. We were testing some properties of this antenna. We already have completed one round of observations last year, and we are right now analyzing this data. This is again low frequency, right from 40 megahertz to 110 megahertz, so covering redshifts from 10 all the way to 30. And as of early next year, we are planning to take Saras 4 to the Arctics, where we will be complementing these observations with 100 to 200 megahertz. And then the idea would be to combine these and look at a joint picture of the global 21 centimeter signal. In the same hunt for better locations, another experiment was born here in 2018 called Pratush. And the reason is simple: independent of where you are on Earth, you will be faced by some or the other sources of interference. In addition to that, you would also be faced by ionospheric effects that continue to be a problem, particularly at low frequencies. And of course, your instrumental systematics are a very strong function of your dielectrics around your experiment. So with all of that in mind, we had proposed Pratush as yet another experiment that will be complementary to Saras' ongoing observations on ground. But this experiment is proposed to be orbiting Moon and conducting the observations when it is on the far side, because Moon is a great attenuator of any radiation, particularly Earth, which is a huge RFI source for us. So that is what it started off with. And as of today, we already have the lab model for this experiment in place. So the system is very similar in terms of its architecture. But of course, it has some unique challenges that even Saras does not have. Everything has to be very compact, very low power. There is a huge metal satellite next to it. So all of that has to be factored in when you design. So you have a revised system, the antenna, along with entire receiver just placed below this antenna. With the lab, we have been able to show that it goes down to the sensitivity of millikelvin across this range. We are planning to operate this between 55 to 110 megahertz. And the forecast with the instrumental properties that we have is that if it is limited by thermal noise, it should be able to detect the huge range of signals that we expect from cosmic dawn. But of course, space-based missions are challenging and the time scales are decades. So we have split this into two different phases, phase 1 and phase 2. So the phase 1, we are proposing to fly in Earth's orbit, well knowing that we will be faced with a lot of radio frequency interference. But taking a pessimistic scenario and basically sacrificing the entire FM band, which we will be continuously seeing in the orbit, we should be able to still constrain a lot of these signals, which are shown in blue here. And phase 2 eventually will be the lunar orbiter, where we have a much wider constraint on a range of these different 21 centimeter signals. And as a precursor to this, we have an ongoing effort led by Bharat here as a RFI monitor in the orbit around Earth, which is supposed to be launched on a PS4 platform in one of these launch vehicles, which is much easier in terms of windows of opportunity to monitor what kind of patches in the orbit are more conducive for experiments like these. Okay, so that's about the intermediate redshifts. Yeah.
Is the point of having it as a lunar orbiter to use the Moon to block background from Earth?
That is one. And the second is the properties of antennas are way more well behaved in vacuum than when you have a dielectric medium around it. So it's a combination of two. And the
orbit is more of a vacuum than lower Earth.
no, vacuum properties would be similar, but RFI will be a major difference. And the second part is, if it is a very low Earth orbit, it may still see part of ionosphere, while lunar exosphere has little ionosphere. So there also you win in these frequencies.
You don't need to point the instrument in any direction.
No. So there is no pointing as such. This is a sky average global signal. But the idea is that you basically want to actively avoid sun. It will complete, the far side will never see Earth, but it will see sun in some time. So your orbit has to be anti-sun. Otherwise your systems get saturated.
How do you maintain such an orbit?
Yeah, so there are, well, calculations of what we call as frozen orbits, which are very low eccentricity equatorial orbits, where, first of all, the evolution itself is not much, the drift is not much, and you get roughly in each far side 20 minutes to 40 minutes sun-free, earth-free times. So those are our best candidates right now for these kinds of experiments.
Are there agreements for the RFI protection on the moon because everything happening there?
Yes. That's a great question and something we worry about, and that's why I think we are a little more nervous on the time scale. Things may just get worse with time. There is a set of regulation that people have been talking about, but to the best of my understanding, they are not binding. And given that there are already experiments around, so we better do it sooner than later. Yeah, thank you. And that's a good segue to just move to much lower redshifts. And this is looking again at 21 centimeter, particularly the power spectrum. But now we are only going to focus on redshifts around 1. And the reason is that the same probe that was a thermometer for your IGM at this frequency is a good tracer of large-scale structure. So in some way, this is a very nice complement to the ongoing galaxy surveys that we have been hearing about. But I still feel that in 21 centimeter, it's even more challenging to be able to do this. And the idea is to look at the power spectrum of 21 centimeter and particularly look at 0.07 to around 0.5 K scales to look at the BAO's primary and secondary tertiary peaks. So for this, I'm involved with an experiment called CHIME. This is in Canada, British Columbia. This is a very non-traditional telescope, very unlike Hera that you saw as dishes. These are cylinders. And it sets a huge field of view, which helps you map the sky very quickly. Almost you get the whole northern hemisphere in one single day, if you use both daytime and nighttime. And then the idea is once you have these maps, you basically do a foreground filtering, get to your power spectrum through imaging power spectra, and look at the signatures of your BAO, which will help you characterize equation of state for dark energy. So this is what a map.
That's a very familiar thought to me, but I've been seeing that, like, I haven't seen that for the past 10 years. And I mean, CHIME has been operating for more than 5 years.
Yeah, exactly. So I don't think, again, we are limited by integration noise, and that, of course, assumes that. And I'll exactly come to that result. We have 2 of them for the 5-year survey of CHIME. This is what the map looks like, taken by CHIME over 1 day. And what you are seeing is the full northern hemispherical sky, thanks to the very wide field of view of CHIME. And a lot of interesting sources, science for many, many people, but nuisance for us. So then we evolve methods to subtract all of this, deconvolve your beam effects here, and get back to a stage where you can look at the 21 centimeter signatures. So the results have been in 2 stages, coming back to your question. The first stage was you take the galaxy catalogs. So this is mostly looking at EBOS. We are looking at quasars, emission line galaxies, and luminous red galaxies. And we are looking at the associated 21 centimeter signatures from these. So you basically stack a bunch of these 50,000 or so galaxies in that catalog and look at if you get a detection in the 21 centimeter. So this is more of a demonstration that CHIME can do 21 centimeter, which is, I think, more popularly known for its FRB studies. And we did that detection back in the 2022, where we look at these catalogs and had around 8 to 10 sigma detection, depending on which catalog you were looking at, in cross correlation. And that really motivated us to now look at 21 centimeter power spectrum in autocorrelation, which is where a lot of BAO possibilities exist. And this is something that happened just this year, as latest as a month ago. This has been a progress for last 6 years rather. This data was taken in 2019, 94 nights. Again, re-emphasizing that this is not integration time problem, this is just systematic modeling problem. But long story short again, we are happy to report in CHIME collaboration we have a detection. This is roughly at 12 sigma of the power spectrum itself. Just like Hera, we don't have access to BAO modes or very low K modes yet, because those modes are majorly contributed and contaminated by your foregrounds. We haven't yet been able to evolve methods that can recover those. So our starting is around 0.4 megaparsec inverse and going all the way to 1.5. What you're looking here is a best fit to the real part of your power spectrum, imaginary part offering you a good validation if you have calibration systematics. I can't go into the interpretation of this, that's a different talk altogether, but you are mostly sensitive to the bias and omega H1 parameters, at particularly the range of Ks that you are probing, which is a mix of linear and nonlinear part of your power spectrum. We also looked at dividing this in different redshift bins. So for example, this is one frequency. CHIME operates in 400 to 800 megahertz. You could be able to divide things. And for this result, we have only used 600 to 800 megahertz, rather 600 to 700 megahertz. And we don't see a substantial evolution in this amplitude parameter between them. This is a work in progress where we now have 6 years of data to work with if we can solve for other other systematics and try to look at more of a redshift evolution for these parameters, but we are not there yet. So with this, I think I'm doing good on time. Okay, thanks. So I'll just stop here and re-emphasize that 21 centimeter signal is a very strong probe of astrophysics cosmology, but right now with the limits that we have, we are mostly looking at astrophysical constraints. And with the upper limits and non-detections that we have already got very nice constraints on a high energy, a high astrophysics universe, particularly in synergy with other observables like JWST and X-ray backgrounds. In particular, the latest results from CHIME, I think will do a lot in feeding back into how the instruments can do better, both in terms of instrument design and the analysis that we have done here. And I think the future really lies in the last, independent of the instrument, unless we really control our calibration and systematics to 1 part in 10 raised to 5 to 10 raised to 6, we really don't have much to go. So this is where most of the efforts is needed, and I think all experiments are gearing in this direction. So with that, I'll stop and take questions. Thank you.
Thanks, Saurabh. Before I pass it on to the audience, I have a comment to make. Your latest venture, Pratyush and I, we share the same names. It's just so strange that I'm hosting you, and my compliments and my best wishes that you achieve everything that you're after. With that, to the audience, Prabha, starting.
So the CHIME power spectrum that you showed had a best fit model. So is that just a fitted curve, or there is some way to know it from theory?
Yeah, I would say this is just a best fit curve. There is a companion paper that is coming out that will talk about this in more detail, but just to show you very quickly what has been done for that best fit curve is your power spectrum is a function of your 21 centimeter brightness temperature itself, which is governed by omega H1, and then you have bias and growth factors. So what you are doing this is you're trying to fit for your omega H1, for your bias, the finger of God effect, and then the transition that happens between the linear and nonlinear part of the power spectrum. So in some way, I wouldn't believe right now much with the, if you have 4-parameter model with this power spectrum, you should be able to do what you have done. But I would encourage to watch out for a companion paper that addresses this more from galaxy feedback models and nonlinear structure formation.
Okay, I'll ask you more later.
So Saurabh, what gives you confidence that the CHIME auto power spectrum detection does not have any foreground systematics left?
Yeah, that's a great question. We have 7 validation tests in the paper, but I'll just highlight a few. One is that we have used a very specific range of declination and array, and in process of going towards the power spectrum, we have done some foreground method, which is a delay filter, along with point source subtraction. So the validation exercises have been, for example, splitting them into sub-bins of array deck to see if we recover the same amplitude. We have also tried relaxing our thresholds for different masks for these bright point sources. And basically every analysis step, The question is, how strongly would it impact your results? And what we find with these set of validation suits, this is a redshift bin, array bin, deck bin, and point source, we effectively recover the same set of power spectra with the same amplitude. So that.
How much of this knowledge can be translated to, I don't know, EOR experiments?
Yeah. So that's where I think I'm most excited working with Hera and CHIME together, because that transfer has already happened. For example, a lot of this delay domain analysis has been motivated by Hera, while CHIME is more imaging based and it's not really a foreground avoidance. But I still very strongly believe the way we have dealt with, say, crosstalk, or the way we have tried looking at the binning of different data sets, I think that has a lot of cross-pollination between different experiments across redshifts. Yeah.
So since we are rethinking cosmology, I guess I'm allowed to ask completely crazy questions. No? So in your hunt for the global signal, I'm struck by the number of exotic places you get to visit: Ladakh, Andamans, Arctic, and now the moon. I'm just wondering, given that maybe one of your main requirements is exposure to the sky should be there. Okay, ionosphere, let's say on Earth, you can't do much about it. And you want a screen against RFI. Have you thought of the caldera of dormant volcanoes as a place to put your instrument?
So I think the closest I have thought about, not definitely this, is having a more artificial location which is more suited for these experiments. So if you go to a radio quiet location that is maybe little more accessible, like Ladakh, I would say here is remotely accessible, but having conditions. For example, we do have a lot of constraint on the kind of ground profile, the stratification that we can live with, or if we are deploying on water, what kind of conductivities we can live with. The idea was to have an environment like that. And I think it's always a question of logistics versus science and where they meet. So not necessarily thinking on those terms, but just logistically, right now it's a big challenge to be able to curate an environment like that.
The moon is easier to reach than curating an environment?
Yeah. Definitely. So, and that's why I think it's not one versus the other. So Arctic and moon can go together. And that reason, I think, is partly driven by the edges motivation, which is when you see something, edges and experiment can do a lot of tests, which they did, and I do commend them for what they did. The problem is you are stuck with your experiment. And some of these calibration systematics are very subtle to decipher. So wherever we be on Earth in Saras and Pratush, the idea is that independent of who sees it first, if you see the same thing in two different environments, that just lends more credibility to things. It's not just logistics.
Okay, hi Saurabh, very nice talk. I think I have two questions to ask. One is about your ruling out of edges result. Did you see anything common in the data between yours and edges? Common in the, if you correlate them, is there anything showing up?
Yeah, no, that's a great question. And I think that's again partly driven because this is largely true for cosmology, which is your results are always going to be model dependent.
Yes.
And we ourselves have shown with the same edges data that one can fit just a very traditional systematic and explain it equally well, if not better, than just a flat profile. So what we ended up doing with edges, if you can see that slide, we took Saras and edges at the same native resolutions. And instead of assuming that there has to be a flattened profile or a Gaussian profile, we literally cross-correlated them, assuming the same complexity for foregrounds. And we have zero correlation.
I see. So, so data speaks nothing about anything on the sky.
Data,
which is common.
Yeah. So this is what I wanted to show. So this is, well, to be honest, we still have done a foreground subtraction. But that foreground subtraction has been common to both experiments with exactly the same model. So what you are seeing on the left is the residuals that you are left with after only subtracting for the foregrounds. And we have shown that this subtraction of foregrounds cannot erase the signal of interest. So you treat them the same way, and you look at the correlations between them. This is over-smoothed signal, and the correlation is around 0.01 or so, which is roughly 98% discrepant from 1. So in that way, it is more model independent.
Okay, thanks. In interest of time, we can discuss later a few other things. Thank you.
Maybe I missed this, but did you see whether the amplitude of a signal, by the way, it's great, very nice results and so on, very impressive. the amplitude of the signal is in agreement with the Meerkat measurements?
Yeah, this is with the chime? Yes, yes.
The
So I
chime,
think
yeah, sorry, the chime. I'm talking about chime.
So largely because Meerkat, I believe, was 0.6 and 0.8, and this is going to 1. We are in broad agreement with those results. Yes.
Okay, good. This is very, very good results.
Okay, Saurabh, before
Yes.
Pratish, don't let me talk. So, I mean, connecting to the NIA question, and I think so deep. So you guys didn't rule out edges data, right? You rule out their claims and their interpretation of the data. Am I right? Because they're using this fifth order polynomial for the foregrounds, right? Which was problematic. And I think you guys used, 2 degrees more. So I think, I don't know if anyone has done a proper inconsistency test between the data, because I think, I don't think that you guys are ruling out the edges data, right?
Yeah, edges measurement is what it is, right? So
Yes.
it is a combination of foregrounds, some residual systematics, a signal potentially, and a noise. So yeah, of course, the data is, it is. Their interpretation was because you could model that your own systematics and foregrounds are still left with something. It was a reverse engineered in conclusion of what can explain that excess. So our thing has been just to take that reverse engineered thing, which is a flat Gaussian, and test whether that is there in our data. So that is one way we have done it, which I would still think is model dependent, because you are testing for a flattened profile and it's a yes-no question you are asking. So you can do base factors and whatnot. But what Shubhadeep asked, there is a model independent way where you don't have to assume something is there, like not a functional form. You basically do a foreground filter on both exactly the same way with same set of parameters.
But you cannot model the foreground completely based on the physical factors, right?
Yeah, so this is empirical.
It would be still empirical or parametric, right?
This is empirical with exactly the same complexity. That's about it. But of course, given that is southern hemisphere and this is northern hemisphere, you really can't do a full physical motivated foreground. But the idea is once you do that subtraction, is there any correlation between them? And that is something we haven't been able to find.
More questions from the audience? If not, we end the session and we thank Saurabh for a brilliant talk.
No, so we take a 20-minute break, right?
Yeah.
Okay. And there are these museum visit slots, which means, I don't know whether you've been asked to sign up somewhere or...
No, I think, yeah. I think just a quick announcement. We do have a museum here hosting a lot of Raman's private collection of rocks and minerals. There is a guided tour which we have planned. So people who want to visit that, you can stay back after the discussion and we'll head from here.
Is this yours by any chance?
No.
I have no idea how this came into my head. Arman, this is yours.
Yes. Thank you.